So here we suppose if without any symmetry, then this stiffness matrix has 21 independent parameters. That is what we know here. Okay, and now we're going to apply the symmetry. Isotropic, that means it's function independent. So let me take one example here. If this is an XYZ plane, okay, and so if we would rotate about the Z axis by any angle theta, let me do this one. Sorry, let me repeat this one. There's an isotropic, that means doesn't matter how you rotate, the properties will be always the same. Okay, so that means the rotations can be applied arbitrarily. So here, let me apply this one first, and for example, this is x1, x2, x3 axis, and then for example, let me apply about the x1 axis in by 90 degrees. Again, this application of the rotation is arbitrary because for isotropic, that means material properties is the same, doesn't matter how you rotate it. Basically, that is the direction independent. Okay, so if I apply this one first, then basically the first application, the rotation of the transformation matrix will be corresponding to this one. That will be equal to, right now we rotate about one axis, and then from here, basically x3 this is x3 prime, and then this is our x2 prime, okay? And this is our x1 prime. So using this way, you can see this will be 1, 0, 0. And x2 prime right now referred to is minus x3. x2 prime is minus x3. Then x3 prime equal to x2. x3 prime equal to x2. So this is such transformation tables applied to our indices. Okay, so for example, this one, if we apply to our calculation Cij KL, let me write it up here. We have the rotations of the stiffness matrix or compliance matrix, and we have such a rule: IJKL equal to LI, LJ, LK, LL, CIJKL, IJKL. Okay, we have such a rule here. Okay, and once we have this one, basically this contents give us is LIJ. Okay, so the information of the L obtained is from this table here, and now what is the fourth order of the tensors? That one we need a word transformation. Again, this is the ad hoc arrangement of fourth orders tensors in a matrix form. So basically this is a convenient, but such a way distract all the beauties of the math. Okay. To utilize this equation, you have to convert this one back to its very original. So this one corresponding, basically if you remember, that relating C111 to this one, basically that is back to the very original, I would say primitive notation is C1111, right? And this one converting is back to the primitive is 1122, etc. For example, this one relating C111 to 12, so that is C1112, etc. Okay? So you convert back to the primitive notation, then you can apply this one, and then part of the homework exercise, doing by hand or doing by program. And unfortunately, I really have a hard time to help debugging the things. Okay? In particular, the 4 layers of the do loop. I'm very sorry, I just couldn't do it. But if doing everything correctly, then you can do this one, okay? So for this case, we apply to this one, then you simply calculate individual components for 21 times. Okay, then you can knock out the necessary information, etc. And so under that situation, then you will come up with is the first type is this. Let me do this. That will become to your handout for the second page. That one will be equal to C11, C22, C12, C12 or 0, 0, 0, and then C22, C23, C24, and 0, 0, and then C22, and minus C24. I think this minus it doesn't matter, okay. And then C44, 0, 0, C55, 0, 6, 5, 5. Okay, this is symmetric. Okay, after these operations, we simplify to such a case, and then we proceed. We, again, for isotropic, that means its function is direction independent. So direction independent, the next one we're going to try is, again, we try in a similar way, x1, x2, x3, and right now I pick rotating by this, about this one, and basically by 90 degrees. So repeating the same process as being calculated on the handouts here, then we can further simplify into oops. Therefore, the material is characterized by okay, let me write it up here. And that is on the page, on your handout, page 5, the bottom of the page 5. So that is C22. I think I missed one page. I think your handout missed one page, and that page basically is this one. So followed by the so your handouts, turn your handout with me, page 1, 2, and turn to page 3. I think follow the end of the page 3 in your handouts. So the beginning of the page 4 must have this one. I'm going to write out here. C11, C12, C12, 0, 0, 0, and C11, C12, 0, 0, 0, and C11, 0, 0, 0, C44, 0, 0, C44, 0, C44. Okay. It is symmetric. Again, this is the form, right? Follow up on the handout page 3. So end of the page 3 will follow this one to start with page 4. I missed this one to you, okay? And again, the derivation is the result combining this and this. And the calculation won't be hard. You can do it, okay? So simply be patient. So right now, after this, then we can count it, and that has 3 parameters. Here, after combining the 2, such the rotation, we come to have 3 parameters. Our goal is 2. Okay, I want to demonstrate the isotropic material only have 2. So the last one. So follow up, the last one I want to apply is this. Because this is isotropic, the material properties are the same for any of the angle of rotation. So now I want to try is rotate about the x3 axis by 45 degrees only and build up the transformation table. So this one, basically here the x1, to here, and this is x1 prime and x2 prime, okay, and this is the x3 prime. So by rotating only 45 degrees, then we can see the rotation table x1, 2, 3, prime, 2 prime, x3 prime, and this is 0, 0, 1. Okay, and this one you can quickly see this will be 1 square over 2 and minus 1 square over 2, like this. Okay, so this is our third and also last operation of the transformation, and try to simplify further for the numbers of the elastic properties. So this one will need a little bit more calculations because this is not exactly 90 degrees, so more non-zero elements will be here, but it's still doable. So the last 2 pages of the handout is providing the detailed calculations. Eventually, what we will come up with is this. The whole element will become again, after operating the whole things and the details showing in the handout, and you will see basically C44 is exactly equal to 1/2 of C11 minus C22, C12. So under this case, successfully we reduced from 3 independent elastic constants into 2. Okay, because C44 actually is the function of the C1112. Okay, so under these situations, we come up with the final form here. Tau 11, Q2, 33, 23, 13, 12. And here we're going to introduce 2 parameters here. And usually people like to define they call the lump constant. So here we only have 2 independent elastic constants. So here in traditional elasticity, the people like to use lambda and mu, and they call the lump constant. And on the other side, using engineering notation, people like to use Young's modulus and Poisson ratio, Okay, so the lambda constant basically defined by this. We define this as lambda. And we defined this as the mu. Okay, so that is the two parameters we define here, and that is very common. If you will see lambda and mu, that's pretty much universal in through almost all the I would say famous textbooks. Okay, so with the two numbers, and we can have the things here. This will be 2 mu plus lambda, and 2 mu plus lambda, 2 mu plus lambda, and lambda, 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 lambda. Okay, so this is 0, 3 by 3. 0, 3 by 3. And this one simply is mu. 0, 0. So this is string x of x. 1, 1, 2, 2, 3, 3, 2, 3, 1, 3, 1, 2. Okay. The whole thing is sometimes people like to come up with very concise writing. So basically, in terms of the symbol, the notation symbol, how I did will be equal to this. If you remember our notations before writing up this one, let me remind you our notations. In the chapters of the string, we have introduced the string invariant. Invariant, invariance, ANT, right? We have three string invariant. The first one, I use this one, I1, and that one basically is a summation of the normal string. And we have I2 equal to something, and we have I3, right? Refer to our lecture notes there. And we call the string invariant because the under different, doesn't matter under which coordinate system we describe, the term, this is constant. Doesn't matter about the transformation of the coordinate system. So that's the reason we come up with this one. With that notation really, then the very concise writing of such a big matrix notation can be written like this. Lambda times I1 times delta Ij plus 2 mu epsilon Ij. And let me check this one with you guys. Based upon these equations, may I do this one here? For example, say when Ij equal to 1, 1, we see. So lambda times epsilon, and then you write it out here. Delta Ij equal to 1 when Ij equal to 1, okay, and then plus 2 mu. Epsilon 1, 1. Okay. And you see this basically this result equal to the first line equations here. Right. Then we can check when Ij equal to 1, 2. Okay. So when Ij equal to 1, 2, then basically delta Ij, delta 1, 2 becomes 0. So the first term is 0. Only have the second term here. You good? Okay. Then you can repeat calculating, you can exercise by changing the Ij only to whatever the substricts here we're showing. You can see this is the right expression there. Okay. So basically either this equation or this equation is called the generalized Hooke's law for, generalized, the three-dimensional, okay, for stress strain, for isotropic materials. Sometimes people like to use generalized, sometimes people use three-dimensional, and the two terms are swappable. This form is mostly widely used in most of the fundamental mechanical material problems because it's simple, and everything for all the details work we might be able to start from this simple model, and then if needed, then we gradually release, go back to the more complicated material properties here. Corresponding to engineering notations, last one. So this is the kind of the first conclusions of the isotropic materials. Any questions before we? Yes.
So, looking at tau 1, 2, there's a 2 in front of, or at the bottom right here.
Tau 1, 2.
Just when you write out the Hooke's law.
Okay.
At the bottom right here. Tau 1, 2. There's a 2 in front of the mu. So how does that relate back
yes.
to?
Okay, let me try this one. So that is lambda times I1 times beta 1, 2, and this one is equal to 0.
Okay.
Right, and plus 2 mu and lambda 1, 2 here.
So where's the 2?
Oh, I missed. That should be 2 here. Thank you so much. We'll back to the correction. Because in my notes I put the scalar of 2 to here.
Okay, but it doesn't matter.
Yeah, I missed it. Sorry. And I think that's a good catch. Okay, so so that is the first conclusion. And based upon this form, I want to have more derived properties for isotropic materials. Okay, so that one will be in this section. So Max, we can have a new section here.